Okay, so thank you for inviting me to be part of this webinar. I'm going to talk about hyperglycemic reprogramming base excision repair. This is a project that is a work of an outstanding graduate student, Griffin Wright, in my lab, who's now Dr. Wright. And we were interested in looking at base excision repair defects in triple-negative breast cancer. And so I don't really need to tell this audience what triple-negative breast cancer is. It's a more aggressive subclass of breast cancer. It's more likely to recur after treatment, and it's often diagnosed at a higher grade. Because it lacks the molecular targets common to other breast cancers, we have to find better therapeutics, better molecular targets. But one of the interesting things you find in clinical data is that there's a prevalence of defective DNA repair pathways, but they're largely uncharacterized. And these are in sporadic TNBCs that don't have classic HR mutations through BRCA1/2. So we were interested in understanding these DNA repair defects. There we go. And so what we performed is a host cell reactivation assay to look at different DNA repair pathways. We saw defects in base excision repair and nucleotide excision repair pathways, but in particular, the base excision repair pathways showed a lot of defects in a TNBC cell line panel. And what we see is almost all base lesions that base excision repair pathways recognize have less repair than you would normally see in a normal cell. And so we see this phenotype of a repair defect, despite the fact when we look at the gene and expression profile of these proteins in the pathway, high expression of these proteins. And so there's a real disconnect between what's going on. And when you look at the major players in the base excision repair pathway, there are a lot of points where things can fail. But what's interesting is we see overexpression in the middle part of this pathway, which is the excision, scaffolding and signaling and recruitment steps, and then the end tailoring and gap filling. So it's really the repair process itself that seems to be dysregulated. And because of their interest in PARP, there's also a lot of interest in XRCC1, which is a non-enzymatic scaffolding protein that's really critical for shepherding the repair in the base excision repair pathway. And so we decided to look at XRCC1 more closely in TNBC. And we looked in other cancers first, and what we saw is if you have a dysregulation of XRCC1, a phenotype of overexpression, you have poor outcomes in other cancers and chemo resistance. So ovarian, colorectal, and gastric have all shown this phenotype, but it hasn't been looked at closely on breast cancer or triple-negative breast cancer. So when we looked at how you could get dysregulation in this pathway, surprisingly, the transcriptional mechanisms for XRCC1 weren't well mapped. But what was clear is both the basal and the E2F1 transcriptional mechanisms used were responsive to endogenous and exogenous DNA damage types. So what we thought we should look for is a dysregulation in a transcription factor that would be responsive to exogenous or endogenous agents. And when we comb back through the literature, there is some evidence for a transcription phenotype with these agents, particularly epidermal growth factor and glucose, but no transcription factor has been mapped back to them. And so when we took a closer look at the XRCC1 promoter, we saw a potential STAT3 binding site. And this fit well with the evidence that we saw in the literature because both EGF and IL-6, which can be stimulated by glucose, activate STAT3, which could dysregulate XRCC1. And so we validated this in a triple-negative cell line model. And what we found is that there is indeed a STAT3 binding site in the promoter of XRCC1, and we can pharmacologically knock down and validate that this site is real. We also validated it in a non-tumorigenic HEC293 cell line. But what was interesting is that in triple negative, you tend to have constitutive activation of STAT3. You have high levels of activated STAT3. In HEC293, activated STAT3 is very low, so we had very low occupancy of STAT3 at the XRCC1 binding site, which we could only manipulate by atopic expression. So XRCC1 is dysregulated in TNBC model cell lines through this activated STAT3. And so we performed a lot of testing, which I won't go through, to validate that IL-6 and EGF actually activate phosphorylated STAT3 and result in increased XRCC1 in both the TNBC models and the non-tumorigenic cell line. And we bring it all back together, why would this matter? If you have overexpression of XRCC1 in other cancers, we see chemo resistance. When we do this in triple negative cell lines, we see the same chemo resistance phenotype. So XRCC1 overexpression independent of STAT3 gives us chemo resistance to carboplatin and also doxorubicin. When we do atopic expression of STAT3 or IL-6 activation, we get the same chemo resistant phenotype. So I want to bring it back to glucose and obesity since that's what we're interested in. So could high glucose be doing the same effect? We saw some evidence of increased mRNA expression, but it wasn't linked to STAT3. So we linked it to STAT3 in the HEC293 cells because we don't have that high constitutive activation. And what we saw is increasing the glucose content in the cell, increased activated STAT3, increased XRCC1 mRNA levels, and also protein levels. And we get the same phenotype of chemo resistance, but we looked more specific to base excision repair with MMS, which is the model BER agent. So increasing glucose gives us a competitive advantage in repair. And so we validated that this is really a STAT3 mechanism by inhibiting STAT3. So when you do the glucose, you get the stimulation, but if you eliminate STAT3 from the pathway, XRCC1 goes back down. So why would this matter in obesity and hyperglycemic type 2 diabetes and these cancers? Well, if you chronically stimulate glucose, you're going to chronically stimulate the STAT3 activation pathway, and you're going to end up with dysregulated XRCC1. And so when we do this in a non-tumorigenic cell line, we can very effectively increase the expression of XRCC1 sustained in cell culture media with high glucose content. So you can systematically reprogram this pathway to give you high levels of XRCC1 over time, which is going to change your sensitivity to DNA repair, and it's also going to change your sensitivity to exogenous agents. And so we do see the same thing in the triple negative. The effect is more blunted because we still have that activated STAT3 present, either through the EGFR mutation or through other mechanisms in these pathways. But what's interesting here is that if you glucose restrict, you can partially reverse the process. It's stronger when you don't have constitutively active STAT3, like in the MDA231s, but this might be why caloric restriction or high glucose treatments actually help improve treatment outcomes for patients or slow tumor growth because you lose this competitive advantage. So what we found was that STAT3 regulates XRCC1. I think glucose is an interesting aspect of this pathway. We don't know the precise mechanism, but it's clear that hyperglycemia and hyperglucose conditions in vivo can cause this. We do have some in vitro, in vivo crossover evidence, but we're still building with that. But it's clear dysregulation of XRCC1 can come through STAT3, particularly in triple-negative breast cancer. Likely other BER proteins are dysregulated in this pathway. And I think once we do more work in relevant model systems, this might offer new molecular targets for breast cancer and help us understand chemo resistance and genomic instability under obesity and type 2 diabetes conditions. And so I'll just thank Griffin and my lab who pioneered this work and the funding that we have, particularly from the Breast Cancer Research Foundation of Alabama, which funded this.
Very nice work. Thank you so much for this presentation. What we are going to do is have the first group of 3 talks, and then we're going to ask the audience to write questions in the chat box. But if there are any questions from the other speakers, I can just repeat them for the audience. We can do that either after each presentation or after the first 3 presentations. What's your pleasure? I can do it either way. Okay. Hearing none, I think it's probably better to have questions after each presentation so that people don't forget. So you've seen an increase in phospho-STAT3 upon exposure to glucose. Does it require intracellular transport of glucose? In other words, does any of the GLUTs participate in this mechanism of the glucose transporters?
So we've looked at that indirectly through glucose changes in the media. So we do see decreases in glucose in the media. So it is being uptaked, but we didn't see any dramatic changes in GLUT1 or GLUT2. That doesn't mean it's not happening, but those are highly expressed. But we can test the media and see that the glucose is being utilized. I do think there's asymmetric utilization. So once you kind of exceed a threshold in hyperglycemia, the cells seem to want more glucose, so they uptake it. So there is kind of like a low glucose to high glucose transition where the cell switches its metabolic phenotype to be more glucose dependent. And I think that also feed forward the process of reprogramming.
That's important because, as you know, a new class of anti-diabetic drugs are glucose transport inhibitors. So maybe these agents could be used to downregulate the STAT3 pathway that you have discovered for therapeutic purposes, to improve the sensitivity of triple-negative breast cancers to radiation or chemotherapy. And the other question is, as you know, triple-negative breast cancer is a very heterogeneous disease molecularly. The MDA and B231 line represents a particular subtype of triple-negative breast cancer, and it also carries a KRAS mutation, which is not very common. So have you looked at other models and ideally patient-derived models?
We haven't looked at patient-derived models yet. We are looking in syngenic models now where we can get the systemic hyperglycemia. But we have done some TMAs where we look at the distribution of phospho-STAT3 and the XRCC1 concordance. And it looks like, you know, obviously the borders with the stroma are where you see a lot of activated STAT3. So it's heterogeneous is definitely going to be an issue, but I think that it will be a robust phenotype for probably luminal type triple negative breast cancers.
Thank you so much.
Thank you.
Are there any other questions for Dr. Gassman? I don't see. Go ahead.
This is Ren from University of Kentucky. I'm sorry for missing the first part of your talk. I'm just curious. So what do you think that the upstream factor that induced the STAT3 phosphorylation? Is that JAK or something else?
So we looked at a variety of cell lines, and what we really thought was going to be was IL-6 and the IL-6 receptor, but surprisingly, the timing doesn't work in some cell lines. So I think it might be cell-specific what the upstream factor is, so that is something that we have to dissect. It looks like in the TNBC models, the MDA468 and the 231s, it looks like it's IL-6 related because we have high IL-6 related receptor and high circulating IL-6. In other tissue types or maybe other breast cancers with lower IL-6, it might be more JAK mediated. So that's something we have to do kind of cell type specific analysis on.